and I'm really happy to introduce Forrest Lacey today. So you all know Forrest, I guess. So Forrest received his undergrad degree in mechanical engineering from Kettering University in 2006. So something interesting. He started working as a product engineer for an automotive supplier. So Born Warner, with a focus on design of variable engine timing devices that are currently installed in a number of cars. That's pretty interesting. So in the fall of 2011, he started his grad work at CU Boulder under David Hensey, where he shifted his focus to modeling of air quality and its impacts using GeoSChem model. His work with this model has continued into his postdoc position at NCAR, where he has also started to work with CAM-chem to understand the climate and human health impacts of anthropogenic activity through ambient air quality. He started his NCAR ASP a year ago, 2018, and he's currently working with others to develop a new model framework that allows for CESM to couple with health impact modeling. With that, please welcome Forrest. Thanks, Forrest.
Thank you. Thank you, Ivan. Thank you for the introduction. And I do want to emphasize that a lot of the work and modeling results that I'm showing here are not my own. It's from work with a lot of people, especially Becky Schwantes and Simone and Louisa, that have all helped develop this modeling framework that I hope to be able to implement as a ambient air quality and health impact forecasting and prediction model. And I'll talk to you about how we're planning to do that and show some preliminary results from the model and how we can implement this framework moving forward. So on this first slide, these are some of the latest results that we have using our model. I'll get into a model description, but this is showing surface ozone, which is a health-relevant pollutant. And this is model calculations that are at around 1/8 of a degree throughout the continental U.S. So the motivation for this work is really driven by a number of reports and studies that have looked at how ambient air quality impacts human health. And one of the major studies to do this is the Global Burden of Disease report, which used to come out every 3 years, then every 2 years, and now it's an annual report. But that's basically a report that quantifies all of the available global epidemiological data to quantify the causes and risks that can be associated with mortality. So this chart that I'm showing here is from a China-specific version of this report, where they estimated all of the number of deaths related to specific risk factors and disease outcomes for 2017 in China. And what I want to highlight here is that air pollution is one of the leading causes of death, not only in China, but also globally. And here you can see that in China, it's responsible for around 1.2 million annual premature deaths. And that's through specific disease outcomes such as ischemic heart disease, COPD, stroke, lower respiratory infections, diabetes, and lung cancer. All of these are linked through some studies to air pollution. And I'll get into how that actual framework works to convince you guys a little bit further. And the current estimate for 2017 of deaths from ambient air pollution, specifically from PM2.5 and ozone, is around 3.4 million annual deaths. So like I said, this is not an insignificant number. This is a very large number, and this is a lot of the motivation as to why we want to link our models, our air quality models, to the health community, is to better understand this number of disease outcomes. And one important thing that I'd like to note with this specific analysis, the Global Burden of Disease project, is that the air quality analyses in this work rely on satellite data and their different products for quantifying what a human's exposure is to ambient air pollution. And that becomes critical, and I'll explain why in some of the future slides. So like I said, ambient air pollution for the Global Burden of Disease report uses satellite data products. Specifically, this is a statistical combination of available satellite irradiance, along with surface observations of different pollutants, model results, and other applicable data such as population and land cover. And basically what the output of this satellite data product is maps that are high-resolution surface PM, and this is what's used to estimate the human exposure at the 0.1 by 0.1 degree. So that's around 1 kilometer resolution for these maps. And I do want to cover what models this specific data product uses. It actually only uses 2 models. One of them is being the GeoSchem model to calculate some of the air quality, and then the other model is TM5 FAST, which is a population-based model that really pushes a lot of the pollution into areas where there's high population. So if this is true or not is still something to be discussed, but this is the satellite data product that is used for the GBD reports. In addition to the GBD reports, there's a number of different studies that are looking at how mortality is impacted by different sectors or in different regions, and I've just kind of highlighted some of these here. So one of the major ones is one from Joost Lelyveld, where he estimated the regional and source-specific contributions to premature mortality at the national level. And then there's been a number of other works looking at anything from specific sectors like domestic waste combustion or trash burning to looking at more statistical analyses in specific regions. So there's a paper that Rajesh was on looking at premature mortality in India using WRF-Chem. And the reason that I highlighted some of these papers is these analyses typically rely on chemical transport models, such as GeoSchem, WRF-Chem, CMAC, to provide the pollutant concentrations that are used for these health outcome studies. And there's limitations in the computational costs that drive this. And the need for high-resolution chemistry and also high-resolution air quality often drive the use of regional models with limited climatological feedbacks. So an example of that would be WRF-Chem, which is a model that has a one-way coupling to a larger climate model, but it doesn't have the full global coupling to calculate all of the climatological feedbacks. Excuse me. And so that leads me to the question is, how can we use NCAR models to address some of these limitations that I talk about here and that I'll get into in future, to explore some of the new science that is coming at the intersection of health and climate, particularly if we're looking at future scenarios moving forward. And then I did want to talk about how these health impacts are calculated to give you guys a better understanding if you may not have been exposed to this. And really, they're, in general, for any specific cause, they're calculated using a function similar to this. So here we have the number of premature deaths is a function of 3 different things: the population, or the number of people exposed, the mortality rate, and that's a disease-specific measure, and the relative risk. And again, I'll reiterate, like I did on the earlier slide, specifically for air pollution, we're looking at specific causes. So this is ischemic heart disease, COPD, stroke, ALRI, diabetes, and lung cancer. And in addition to the different causes, we also need information from different regions. So that can either be at the country level, state, county, or municipality. So that the level or your region that you have defined is user selectable and can vary depending on what question you're trying to answer. So I'm going to start with the first part that goes into this function, and that's the population. Population is really available from a number of different data sets, but the one used for the GBD report is the United Nations World Population Prospects gridded population of the world. And this relies on national scale census data combined with a socioeconomic analysis to provide spatially distributed high-resolution population data. And when I say high resolution, that's about, I think it's 30-second resolution, so it's very, very high. and it provides it for each individual country. And the thing that I like to highlight here is that since this does rely on national scale census data, the uncertainty or the level of confidence that we have in population data is much higher in regions where we have good census data. So in the United States and throughout many parts of Europe, we have very high confidence in the spatial distribution of population because we do census based on county levels that then get fed back into this algorithm. But for many other countries, particularly those in Africa, census data is not as precise, and it relies a lot more on these socioeconomic predictors to get the population right. So that's another source of uncertainty that goes into these calculations that we need to account for. The second part of these health impact calculations is baseline mortality. And baseline mortality rates are basically a per capita measure of cause-specific deaths in a region. So this chart here, what I'm showing is the number of deaths per capita for ischemic heart disease. And the top axis, I apologize, it's a little small, is 500 deaths per 100,000 people. And then you can see that this specific analysis that's part of the GBD project calculates it for each of the 21 GBD regions. And I've highlighted where high-income North America is, where we're closer to 200 deaths per 100,000 people for ischemic heart disease. And if anybody's curious, the top region is actually Eastern Europe, and that's not really related to air quality, except they have higher baseline mortality rates to heart disease, mainly due to the prevalence of alcoholism, and that really impacts how many people die from heart disease in those regions. And then, like I said, you can break this data down even further. So here, previously I showed you high-income North America. That's made of 3 countries, the United States, Canada, and Greenland. Greenland is on the bottom, and Canada's in the middle. United States, we're not doing as well for heart disease. So that's something we can obviously work on. And then you can, again, break it down even further and look at state-specific mortality rates. So here, this is all of all 51 states and districts. And as you can see, Colorado's doing pretty well. The top is West Virginia. So don't move there if you. What's the bottom? Alaska, and then Utah is the other one that's beating us. So here you can go from the macro level, which is the GBD regions, which is basically on the length scale of greater than 1,000 kilometers, down to the country level, which is around the length scale of around 1,000 kilometers, and then to the state level, which is around 100 kilometers. And if you start to think about this as the length scale in hundreds of kilometers, this is where we start getting into the resolution of the climate models that we're currently using. So CAM-chem runs at around 100 by 100 kilometers if you run it in a fixed grid setup. That's around the length scale that we're calculating here. And then finally, moving on from the GBD report, and this is especially applicable in high-income countries, is we have even higher resolution data. We're now on the tens of kilometers in terms of the data that we have for baseline mortality rates. This is from the CDC Wonder report for 2017, and this is the calculated baseline mortality rate for ischemic heart disease based on each individual county in Colorado. And you're doing pretty well if you're in Boulder. It's around 46 deaths per 100,000 people. But if you're like me and you live in Broomfield, you're doing even better. That's around 39.5. So I guess the last thing I'd like to emphasize with this is we're really at high resolution data for the other sources that go into these health impact calculations. So if we want to be able to effectively use this data, we really have to have all of our other calculations at the same resolution. And that leads to the final term, which is relative risk. And relative risk is a measure of the increased likelihood of contracting a specific disease outcome due to some attributable factor. So in general, this could be anything. These were first developed back when they were looking at secondhand smoke and tobacco exposure, and they developed this relative risk function for how much more likely you are to get lung cancer or heart disease based on the amount that you smoke or your exposure to secondhand smoke. So that was kind of the baseline setup for developing these relative risk calculations. And these are quantified using cohort studies that create a statistical relationship between a specific health outcome. So in the previous plots, I was looking at ischemic heart disease and some attributable factor. So before that was secondhand smoke, but in this case, we're going to consider this to be ambient air pollution. And again, if we want to look at a specific cause and region, we can have our function be a factor of that, where we now have some spatial index that's a subterm of your region, and you're looking at population and relative risk at those same spatial indices. And then we can expand out this relative risk term that's a function of your spatial index, your cause, and your region to be 1 plus some exponential factor. In this case is a function of your pollutant concentration and some threshold exposure. And developing these functions is extremely non-trivial. And the most well-known version of this was what's known as the Harvard 6 Cities study, where they linked air pollution to mortality in 6 U.S. cities. This paper has been cited, I think, a little over 9,000 times. And basically what they did is they took air quality or air pollution data, and then they created these curves which are for specific disease outcomes. So each line is a specific disease, be it lung cancer, heart disease, COPD, anything like that. And then on the x-axis, you have pollutant concentration. So for this specific curve, that's PM 2.5. We have different ones for ozone. And then you can see that as your pollutant concentration increases, you have an increased relative risk for a specific disease outcome. So here, this is 2. What this basically means is that if you're exposed to around 100 micrograms per meter cubed, you are twice as likely to contract acute lower respiratory infections. So that's how these relative risk factors work. The latest work is using this hazard ratio, which is very similar. One of the main differences, and one thing that I want to highlight is it's extremely non-trivial to generate these curves. You need a long temporal scale of data. This specific study was a 14 to 16 year cohort study. So what they did was they tracked ambient air pollution and individuals and their health outcomes over a 14 to 16 year period to generate these curves. So it's not like you can just go out and generate new curves every year, because you have to have co-located mortality rates with air pollution monitoring. So if you think about regions that we have this temporal location of data, it's not as much, although they are starting to increase quite a bit. Just in the last 2 years, we've actually had specific cohort studies come out from different regions, China being one of them, where they developed their own cohort study based on kind of the higher concentration exposures. If you think about the US, we have relatively clean when it comes to PM 2.5. Many places in China have a little bit larger concentrations. But, yeah.
The air pollution and cigarette smoking, it says there, that's factored in there?
Yes. So the way that they factor in all of the cohort studies from cigarette smoke is those are used to fill in the higher micrograms per meter cubed. So typical secondhand smoke is in the 200 to 300 micrograms per meter cubed. In the US, we don't have cities that are at 200 to 300 micrograms per meter cubed. So they could calculate the relative risk from those secondhand smoke studies and use that to fill in these curves. And then the other thing that I would like to highlight with the more recent data is this is a statistical analysis. And as we add in more data, we basically increase our confidence in the statistical function. So what's happened between this 2014 study and the one from 2018 is we've actually decreased the threshold exposure concentration that we can statistically say is linked to a health outcome. So it was around 7.4 in the 2014 study. We've shown that that's now around 3 micrograms per meter cubed in terms of our statistical linking. Yeah, Chuck?
Just a clarification here, you're talking about contracting a disease, that's the relative risk. Before you were talking about mortality. So is this contracting disease that will prove to be fatal, or is there another variable to get you to the mortality piece?
You need both of them. So if you just quickly go back to this function right here, you need to have a baseline mortality rate for a region. So that's something that varies depending on where you live. But then you also need to calculate what your relative risk is, and that's a function of air pollution. So the mortality rate is just a function of where you live, and then the relative risk is a function of what you're exposed to. So you need both of those.
Healthcare would come in the mortality rate?
Yes, quality of healthcare comes in the mortality rate.
But it's different data sets, right?
Oh, yes.
Data sets,
Yep, these are different data sets.
acknowledging than the disease data sets.
The mortality rates are going to be 100% based on hospitalizations and things like that. So basically what the CDC reports for different disease outcomes. Whereas relative risk is going to be a statistical relationship that's created through these cohort studies that I mentioned before. All right. Okay, and then I mentioned that the counterfactual or threshold exposure is something that's been decreasing as we have add in more data, we have more confidence in our statistical relationship. So this now leads into model development and kind of what is driving the need for a new model. Well, so global climate simulations with full chemistry often require relatively coarse resolution grids to be computationally feasible. And when I say relatively coarse, that's on the around 100 kilometer scale. So it's not super coarse, but it's relatively coarse if you're talking about health impact calculations. And if you're thinking about that scale, for exposure, resolving gradients is much smaller scales than what you see in the 100 to 150 kilometer is needed. And this is kind of what I'm showing here. This is around a 100 kilometer grid box over Italy. And then you can see that you have pretty large gradients in terms of the PM2.5 within that individual grid cell. So previous studies have used satellite downscaling to accomplish this, where essentially you break this down into the satellite components and redistribute your calculated PM2.5 to this higher resolution, and then that allows you to calculate the exposure level concentrations. The problem with this is you have to have satellite data in order to accomplish this. And it really limits the analysis to, one, time periods where there is data available. And it also can't account for changes in speciated PM2.5. What we're getting from the satellite data products is the total particulate matter. But that doesn't tell us anything about how black carbon is changing relative to organic carbon. So if we want to do anything that's a specific subset of total PM2.5, it becomes more challenging to redistribute the PM2.5 using satellite downscale. And then the temporal aspect of it is, one, we can't do future simulations, but also anything that has a kind of extreme events or type of diurnal cycle, we typically don't have satellite data that encompasses that yet. That may change as we move to the the geostationary satellites, but currently we do not have that as a data set available for analysis. And this kind of leads to the question, how can we approach these issues within a single simulation? And this little bubble plot is something that I'm sure all of you have seen a number of different times in terms of the music of development. And this is the current framework of NCAR's CSM model, along with any other Earth system models. And I kind of break down the atmosphere model into two things. One, we want to have full chemistry. We want to resolve all the chemistry in the atmosphere. That leads us to CAM-chem. And then we also need to resolve the dynamics in a computationally feasible manner. And currently, we're doing that using either the FV dicore or the SE dicore, where FV is a fixed grid, SE is a cube sphere. And the current scales that we use with these dicores are most applicable to climate modeling, and they require improvement if we want to look at health impact calculations. So this has basically led to the development of what we're tentatively calling Musica version 0, which is a global atmospheric chemistry model with regional refinement. And here I'm kind of showing what that means, is you have a global cube sphere grid, and then you break that down into smaller and smaller scales over a particular user-defined region. And what we've done for our preliminary calculations is we've gone from around 100 kilometers global, and we refine that down by a factor of 8 to 14 kilometers over CONUS. This is ongoing work. It's a heavy collaboration with CGD. And the reason that we're going down to 14-kilometer resolution is because, one, the chemistry is more accurate or more accurately represented. And then pollutants are also simulated at human relevant scales. And we're also including these global feedbacks that we get from the global climate model. And then I mentioned that both PM and ozone factor into the health impact calculations. And I just want to show some initial results with ozone because that's something that we're a little bit better at working with. We've done a lot more validation on it. And it's also something that's really spatially heterogeneous because the emissions of different pollutants and then the factors that go into ozone formation really have a large impact when you move to smaller spatial scales. So here we have isoprene emissions in the model, and we're doing a comparison between the SE 100-kilometer grid and our regional refined grid, and you can already start to see the spatial differences. And then again, we have NO emissions, and the addition of sunlight leads to higher resolution of our ozone concentrations using the regional refined model. So at the top, we have the 100-kilometer spectral element, and we're already seeing improvements in ozone concentrations using the regional refined model. And the main goal behind this is to connect with the health community, as I mentioned before. And there's two specific factors that I think we want to capture with this model. One, we need to have exposure-relevant scales. And two, we need to have the global climate system feedbacks. And the current iteration of the model captures both of these. So here, we're looking at the Southern California seaboard, where we have San Diego, Los Angeles, and Santa Barbara. And you can see what was 3 grid cells in the SE model. We now have a number of different grid cells calculating the different impacts there. And then from global and regional climate feedbacks, what you're going to see here is tropical cyclone formation, pulling polluted air from Mexico City, which eventually makes landfall on in New Orleans in the Gulf of Mexico. I'll play that again real quick. So you can see polluted air gets pulled into a tropical cyclone, and it's important to note that you don't see that at all if you go to the 100-kilometer scale. So, So this model currently addresses both of the limitations that we need for health impact calculations. And the overall goal that we have with the model is to develop this as a chemical forecast and prediction framework that captures all of these different things. And it also provides us the opportunity to calculate human exposure where we may not have the appropriate satellite data, which I highlighted earlier is something that's very important moving forward. In addition to ozone, the other health-relevant pollutant, is PM 2.5. And this is the simulation that I'm showing right now we have model predicted PM 2.5 at the 14-kilometer scale. And you can really start to see how small-scale dynamics come into play. You can see different weather fronts impacting the transport of pollutants or the stagnation of air and transport of different things. And one thing that I want to show, or I guess first I want to mention that this version uses a modal aerosol scheme where we have 4 different aerosol modes. And it's already starting to show the importance of high resolution, both spatial and temporal inputs on modeling ambient PM 2.5. By the end of the year, we have some development goals, which are to update the aerosol scheme. Basically, we made some improvements in CAM-chem. We would like to get them into the regional refined model. So that would be the addition of nitrate aerosol, and also expanding the modal scheme and potentially implementation of a sectional scheme. And then we also want to use model results with health impact functions, which is something that I'm working on right now. And one thing that I want to show with this model result right here is different regions, and you can see that the transition zone. So right here, these 2 boxes, the top one is in an area where we're transitioning between regional refinement, and then the bottom one is fully within the regional refined region. And here you can see the coarser resolution. These are both biomass burning events. You can see the coarse resolution emissions and transport, and definitely compared to the high resolution within the regional refined region, we can see more thorough quantification of the transport and pollution from this isolated event. So that was some of the preliminary results. I also want to get into what we've calculated for exposure, because I think this is really neat. And just want to talk about the model setup that we have. These are all of the terms in CAM-chem that you need to prescribe if you want to build and run the model. So the specific grid is the NE0 CONUS NE30 by 8. And what that means is that's a base NE30 grid with 8 times magnification. And moving forward, that's going to be the nomenclature that we use if we want to do a different model simulation. So if you wanted to do NE30 by 16, that would be 16 times magnification in the user-defined region. One important thing to note that we've just this week found out to be extremely relevant, or sorry, last week to be extremely relevant, is that we actually have to use a high-resolution land model output with this. Otherwise, there's some impacts from topography that significantly impact precipitation, vertical transport. So that's why the land grid here is the MT12, and that's a 0.1 resolution land grid instead of the standard 100-kilometer land grid. And for emissions, we're using anthropogenic emissions from the NE 2014 inventory. And then outside of the regional refined area, we're using CMIP6. Biomass burning, we're using FIN 1.5 globally, and the biogenic emissions are calculated from the land model. And now I want to kind of show you the results from, basically we took one simulation and regridded it to various resolutions. I'll show you the impact from here. So this is looking out over Seattle, where we have aggregated PM 2.5 to the 1 degree, the model output at the 8th degree, and then I'm showing the satellite PM 2.5 for the month of June 2012 as a comparison point. And what we're going to do is we're going to look at this specific region that encompasses 4 1-degree grid cells. So here, I've rescaled it, and you can really see how the resolution impacts the distribution of PM 2.5 moving throughout the area. In the 1-degree model, this is only 4 grid cells. But as we go to the 8th degree model, that becomes increases that by a factor of 8. And then the satellite data, as I mentioned, is at the 1 kilometer resolution, so that's what we're showing here. And then what we need to calculate the exposure from this specific model output is population. So here what I'm showing is population that approximately matches our native grid output. So it's at the 0.1 degree. Our model output's at about 1/8 degree. And then how we calculate this is we basically take our concentration from the model, multiply it by the population, and then divide by the total population in the domain. And this gives you the population-weighted PM2.5, which is what we were showing on those cohort curves. So this is how you calculate the relative risk in the model. You have to have some pollutant concentration, some population, and then that gives you the population-weighted PM2.5. As you can see, depending on which model setup we use, we have much different distributions of what our PM2.5 is and how closely that matches the population. And this function is scale dependent and causes difference in exposure estimates. So if you have population data that doesn't match your air quality data, you can have some mismatch there. And I'll show the function of that here. So what I've done is I've done that calculation for just these 4 grid cells to calculate the population-weighted PM2.5 in this 200 by 200 kilometer box. And here we're seeing that we actually get differences in what the population-weighted PM2.5 is between the aggregated results, the native resolution results, and then the satellite-based PM, the high-resolution data. I do want to note that with the satellite data, I had to aggregate that to the population scale. So there is going to be a lot of mismatch there, and it will definitely change if I used higher resolution population data. So that really shows the impact of using data that matches each other wherever possible. But the interesting thing to note here is we actually see a difference in exposure just based on how we aggregate our PM2.5 between 2 different models.
Can I ask them?
Yeah.
The blue in the satellite data, is that no data, missing data?
It's below 3 micrograms per meter cubed.
So they're completely...
And then the gray is no data because over ocean they don't have.
Okay, so all 3 don't agree at all. Basically.
Yes. And the reason for that, I still need to look into that further, but we could have a biomass burning event in the model that's not captured in the satellite data. There could be a number of other factors that attribute that. And it does bring up one of the limitations of the satellite data sets is the TM5 FAST model really scales your surface PM2.5 by population. So what that doesn't do a good job with is some of the biogenic aerosols, so sea salt and dust. In this case, it's probably sea salt. So you can see that large area there. That's potentially sea salt or biomass burning event. I need to look into it further.
Same day?
This is the month of June.
Oh, this is
averaged.
An average.
Yeah, so all of this is the month of June 2012 averaged.
Okay.
But you should also point out, I mean, this is not actual satellite data of
No.
PM2.5.
Right.
This is a derived product after it's been gone through
And that's,
several times.
yes, and that's why I bring up the TM5 FAST model. That spatially allocates a lot of the irradiance data to areas where there is population. And we just don't have the satellite data to show that that's actually the surface PM concentrations. It relies on those model outputs along with observations where we have them. So it's not a pure satellite product. This is not a pure satellite data set. This is a reanalysis product that includes a number of other systems. And we actually have a paper that's in review right now exploring how the differences between a lot of these different satellite data products and kind of showing how they differ depending on what data set you use and which reanalysis framework you use. And then I also want to show the other part of the validation that we're doing, and this is just comparing the results between the 1 degree model and the regional and refined model. And here, what I've done is I've calculated PM2.5 now in the NE30, which is the 1 degree SE grid, versus the regional refined NE30 by 8. So here we have, apologize, I forgot to throw it on here. This box here is the 1 degree model. This is the regional refined model. This is absolute difference and then percent difference. And what I've done was I've calculated the PM2.5 between all of these for each different model. And then this chart here is showing the difference between the SE and the SE regional refined for each EPA region. And it shows it a little bit better here. So here, we're getting up to an 8 microgram per meter cubed in population-weighted PM2.5 difference just between the 1 degree model and the regional refined model for each individual EPA region. And then now we're showing the difference histogram. That's the factor that they're different. So it goes up to a factor of about 0.5, both in the positive and negative. So that's a 50% uncertainty depending on what model iteration you use. And I've again repeated this analysis, except now I calculated the population-weighted PM2.5 at the state level. So if we were calculating individual states and what the mortality in that state was. And again, we see very similar ranges of differences between the SE 1 degree and the regional refined. So here we have absolute differences going up to 10 micrograms per meter cubed, and the factor difference is going from around negative 0.8 to positive 0.6. So these are very large uncertainties depending on your choice of model resolution. So this, I would basically say, is a kind of a caveat when you're looking at health impact studies. Make sure that you understand what's going into the air quality analysis side of it. And then I did want to link this back to the relative risk. So here, if you're looking at around a 10 microgram per meter cubed change, that can be up to a 10 to 15% change in the actual health outcome. And what I mean by that here is if we start at the threshold exposure, increase that by 10 micrograms, we're up to around a 1.15 relative risk factor. So this ends up being a large health outcome. And like I said, really consider that when you're looking at what model PM2.5 goes into these analyses. And we're doing the validation of the model right now to confirm that the high resolution model is a better predictor of PM2.5. And we'll look forward to that moving forward. And then I just wanted to highlight some of the future work and uncertainties in this analysis. One thing that we're trying to do moving forward is use tag tracers for source contribution of PM2.5 exposure. So this gets at that one question that I brought up with the satellite data. That's for total PM2.5. So if you want to look at a specific subset of PM2.5, you have to use some sort of either an adjoint approach, or we can use tag tracer finite difference for this. The regional refined model does potentially still have some issues with scale-dependent parameterizations, particularly something like dust mobilization or sea salt emissions. And that's something that we're validating more moving forward. And finally, we're going to attempt to collaborate with the health community using the CMIP6 experiments that move through the 21st century with regional refinement to better quantify what basically the uncertainty of future ambient air quality exposure is. And with that, I'll take any questions.
Great, thanks, Forrest. Are there any questions?
No, he's got that.
If you go back to where you had the histogram, the PDF, the differences with the resolution.
So the state one, and then do you want state or EPA region?
That one's good. Okay. So the difference histogram seems to be biased towards positive values. Do you understand why that would be, and do you think that's a true improvement, or?
It's something that we're still evaluating more, especially from the PM side. And it's going to come down to what sources are causing this. So basically what I want to do is create this histogram, but now for each subset of the PM2.5 to find out if I would expect it to be this way, where we're biased high in the, sorry, I'm trying to remember exactly what I have here. This is, okay. Yes, so this is, what it's showing, the absolute difference is regional refined minus the coarse resolution. So we would expect the regional refined to predict higher for anything that's over a population center, whereas with the coarse model, basically you get mixing over a really large area. So that would be anything that's like a local urban impact, whereas we would expect it to go the other way with kind of distributed emissions, so things like biomass burning or things like that. So that's why it's going to be a source-specific answer, and I just haven't done that analysis on that yet. So I could see it going either way.
Yeah, just it's all pretty interesting stuff to me. But my question has to do with sort of the exposure side.
Yep.
And the relation between how the relative risks were and mortality was ever developed from like personal exposures versus what,
yes.
I mean, and so what you're looking at is everything that's outside, whereas we live most of the time either inside or in a car,
right,
rather than walking around outside. So what's the relationship between sort of actual exposure and the need to refine the level of chemistry and what you're trying to work on here?
Yes. So personal exposure is another side of it, and I didn't mention this previously. Excuse me. But the GBD report does break that down into indoor exposure versus ambient air pollution. So the functions that we're using are specifically tied to ambient concentrations. So this, the Harvard Six City study, they used, I'm going to find out where I put it. There we go. They used ambient concentration. So this is just a statistical relationship between health outcomes and ambient concentrations.
Independent of what the other parts?
Independent of your household exposure. Yes.
So I'm just curious, actually. So you compare these different resolutions, and there's a big difference. When you compare with the satellite data, which is 1 kilometer, right? There is a factor of 3 difference in the estimate. So what would you say is the reasonable resolution for modelers to consider in the future? It seems like 10 kilometers is not enough.
Well, I think that there's also limitations that have to be factored into is what resolution can we effectively resolve the dynamics. Like we can't really go to 1 kilometer and still resolve kind of the transport problem. That would be more of like the eddy scale, so that gets down to higher resolution, different models that you have to use, that then become more computationally intense. And I would also point out that this specific factor of 3 difference between the satellite data product, that was just for 1 month, and it was a specific satellite data product. I think that range may actually be a little bit smaller as we evaluate more data. I would expect that to be, based on some of the previous work that I've done, I would expect that to be kind of on the factor of 50%, not a factor of 3.
So would you say that actually Lelyvel's numbers in terms of global mortality are actually way overestimated? I mean, 50% overestimated.
I think his latest numbers are high, yes. I do not believe that the number of deaths from ambient air pollution are 8.8 million. I don't believe that.
Why not?
Well, because that study specifically used a 1-degree model to calculate exposure. And he stated that the impact of modeling your PM2.5 at a different resolution is negligible. We've already shown that there's differences between what exposure is calculated based on your model resolution. So I find it hard to believe that it's a negligible impact when I've shown that it's a 50% or more impact.
But you think it's lower, not higher. Could be higher, right?
It could be higher.
I mean,
that number.
I can see this overlap between population and going either way. For example, you have your dose response curves as a function of PM. They start out steep and then they flatten out.
Oh, yes. Yeah.
So if you're artificially diluting, you are moving from the saturation region into the steep sensitive region.
Yes.
So artificial pollution in this case, for this factor, would tend to give you more.
Yeah.
On the other hand, population and pollution tend to be co-located, and that by itself will give you more when you compress rather than dilute when you do high resolution. So it can go either way.
Yep, it can go either way, just based on my analysis using, this was not in CAM-chem, this is using GeosChem. I evaluated the health impact using different satellite data products. So specifically, the Aaron von Donkelaar product uses TM5 FAST that attributes it to population. If I use a different one that uses a geographically weighted regression that's more tied to land cover type, there I noticed a really big difference in what the health outcomes were. And that's in the paper that we have in review right now. But just based on that analysis, I would expect it to be lower. We have one more question.
Okay, so Forrest, great work.
Yeah.
One of the things so there are two uncertainties, one in the air quality simulations, and then you have also uncertainties in these dose response curves.
Yep.
So these are these are built on observations in the US, and means I don't have much experience in this area, but the limited studies I have been involved in, one of the questions that reviewers always ask, how representative are the dose response curves, say for example for India and China?
Yep.
And the easy answer is that, okay, this is the best information available, so we use that.
Right.
So in your opinion, what is more important in terms of uncertainties, the uncertainty related to the dose response curve or the air pollution estimates?
So that, I think, it's going to be, depending on what region you're looking at, what becomes the driving uncertainty. If you're looking at something like Africa, I think the largest uncertainty there actually becomes the population. Whereas if you're looking in China, I think in China it's going to be the air quality concentrations. In the U.S., probably the driving factor is going to be your dose response function, because we have relatively good quantification of what the pollutant concentrations are. Whereas in China, depending on what season and where you are, you're all over the map on this dose response curve. So that becomes a really large factor in the uncertainty. So it is a region-specific question. And we are starting to get, like I mentioned, we are starting to get these dose response functions from other areas, not just based out of the US and Europe. The GEMS paper here actually includes some of the cohort studies from China as well. So this is the latest kind of hazard ratio that they've developed, and that includes China-specific cohort studies. So we are starting to get that information now that they've basically been evaluating air quality for the last 8 to 10 years. They can develop these cohort studies.
I think we have time for one more question.
I'll ask a silly one. If satellites can measure aerosols from space, a few micrograms per cubic meter, why can't they measure how many people there are? Maybe they are measuring that, we just don't know about it.
There are specific, Africa-specific estimates of population that rely on nighttime irradiance. So basically they're saying where there's light, there's people, and then they use that to quantify population in remote regions. So we are kind of doing that already. By we, I mean not me, but other people. But yes, that is another tool that is being used.
That has uncertainties too.
Yes. Yeah. Yes. Yeah. I think that the key takeaway, if you take away anything from this talk, is that when you're looking at this health impact function, remember that each of these terms has uncertainties, and these uncertainties are not small. I mean, we're talking about 50% uncertainties in some cases on each of these. So that leads to a really large uncertainty in the estimated mortality from air quality. And I think that moving forward with this high-resolution model and exploring some of these scale dependencies and how that impacts your health impact functions will help reduce these uncertainties. So it's kind of what we did with the IPCC report, reducing the uncertainties in radiative forcing. I think we need to have a similar approach with each specific term in the health impact function now.
Great. Thanks, Forrest. Please, let's thank again, Forrest.